We all know how complex the Earth is, and this is why we love to explore and study all the challenges that it poses to us. Understanding how this beautiful planet operates only puts us one step ahead of ensuring its sustainability for the generations to come. My name is Abdulaziz, and welcome to our University of Arizona Senior Engineering Design video presentation. Our group, Biosphere 2 Chemical Engineers, also known as B2Chi, is composed of 4 creative, talented, and outgoing chemical engineers. Our first member is the great Omar Al-Ghamdi, coming all the way across the oceans from Saudi Arabia.
Hey Aziz.
Hey Omar. Up next is the wonderful Brooke Rosetto.
Hey guys.
Hey there, Brooke. And last, but certainly not least, the adventurous Michael Coyne.
Hey Aziz, let's get this show rolling.
We certainly will, Mike. Our team was composed in January of 2020. However, we previously worked together on our chemical engineering laboratory class instructed by Dr. Gregory Ogden. Now, we are united again under our amazing chemical engineering senior design professor, Dr. Adriana Brush. Our design project proposal was obtained from Biosphere 2 to upgrade an existing system that is currently located at the Biosphere 2 facility in Oracle, Arizona. Omar, would you like to run through what Biosphere 2 is and our assigned task?
Of course, Aziz. Biosphere 2 is such a complex Earth and science research facility. Biosphere 2 is located in Oracle, Arizona. The project started in 1984 to study the effects of living in outer space by creating a closed system where humans may live without contact from the outer world. In recent years, B2 changed its mission course. Biosphere 2 embarked on a journey like none other in 2012. The Biosphere 2 team designed a process to study how the landscape is affected by physical and biological processes. This project was built in collaboration with the University of Arizona, M3 Engineering, and various other partners. In 2015, the Landscape Evolution Observatory, known as the LEO, began operations. A simplified version of how the LEO operates is it rains on a hill slope. There are hundreds of sensors embedded into the LEO study a variety of variables as they detect the tracer which is injected into the water that is rained. It's crucial to note that the LEO is a single ongoing operation, meaning it has not been shut down since it's first operated in 2015. You might ask yourself now, how are we able to add, remove, fix, and test processes and ideas on a system that does not stop? Well, this is where the mini-LEO comes in. The mini-LEO operations are similar to the LEO, but on a much smaller scale. Our task assigned by mentor Wearing Nick is to upgrade the mini-LEO setup by modifying various parts and components to the current system. Additionally, we aim to design a tracer injection system that is compatible with the lithium chloride tracer. Brooke, what do you think of the current mini-LEO setup?
Omar, I believe the current system performs a good job for the price it was built at. However, as the Biosphere 2 advances in LEO testing stages, it's crucial to upgrade the mini-LEO system. As Omar mentioned, the mini-LEO performs the same fundamental processes, which is raining on the hill slope. The rain contains a tracer that is detected by the sensors embedded into the hill slope soil. Therefore, the researchers are able to study and identify the functionality of various tracer to later rain on the LEO. We identified the rainfall distribution from previous tests conducted at the Biosphere. As the heat map shows, the rain is not distributed uniformly. The current injection system is incompatible with the lithium chloride tracer because of the metal parts and components in the system. We had 4 months and $5,000 to come up with a design, and that we did indeed. Wouldn't you say so, Mike?
I 100% agree, Brooke. We achieved this by beginning our design process performing preliminary research. This task simply consisted of asking the mentor questions about the process and learning about the LEO and mini-LEO. We then performed additional in-depth research where we were able to identify the constraints, criteria, and possible solutions for the project. As Brooke mentioned, the time and cost constraints were set to 4 months and $5,000. So, we needed to act fast and efficiently. We were able to identify some of the major constraints provided by the Biosphere 2 that were crucial to remain in the upgraded design. This consisted of a flow meter and sensors embedded into the hill slope soil, the positioning of the mini LEO itself, the height and orientation of the nozzle injection site, and finally, the compatible use of controlling software. Other than that, we were ready to go. In order to deem this project a success, our criteria are as follows. Now, I will let Aziz explain to us how we were able to complete the required criteria while still satisfying all of the set constraints.
Thanks for the great detail, guys. After we identified our constraint criteria and goals, we moved on to develop 4 alternative designs. Design A had the highest cost while Design D was the cheapest. Design A was also the highest performing, with D being the lowest performer. Against all odds, D was selected because, as we will see, this design fulfilled all goals without hurting the wallet. There are 4 major sections of the design: the main line irrigation system, the tracer injection system, the injection point, and the spray system. The main line irrigation system is composed of the following primary parts: a 55-gallon tank, a solenoid-driven diaphragm pump, and a flow meter. Both tank and flow meter are from the existing system, while the diaphragm pump is an upgrade from the current existing air diaphragm pump. Solenoid diaphragm pumps reduce pulsations and adjust stroke length frequency. As we move on to the tracer injection, a newly developed design, we begin with a carboy tank, a peristaltic pump because peristaltic pumps do not interfere with the liquid pumped through the system, a static mixer to ensure uniform mixing before the tracer is rained on the hill slope. Note that the static mixer is also the major component of the injection point. Finally, for the spray system, we studied 2 nozzle heads. The total price for this design, plus all additional accessories listed on the cost sheet provided to Biosphere 2, the total price comes out to $4,300 US. $700 less than the expected budget. We were not able to fulfill the rainfall distribution criteria due to the current nationwide closure of stores and facilities, amongst which is Biosphere 2. However, we developed a plan to test these nozzles, and we will be providing it to Biosphere 2. We were able to successfully design tracer injection system compatible with lithium chloride. These are some of our technical diagrams: injection system process flow and block flow diagrams, entire system process flow diagram and block flow diagram, a piping and instrumentation diagram of the entire system, and an electric version. We would like to thank the Chemical Engineering Department, the University of Arizona Engineering Department, and our sponsors, Biosphere 2. We wish you a wonderful rest of the semester, and remember to stay safe and stay home. Thank you.